In this video, we're going to be discussing how to distinguish between nucleophilic substitution versus elimination reactions. Often, these are competing reactions. In fact, if we look at the structures, say we have an H and an X, in one case, we can do the nucleophilic substitution and be left with a transformation where we've replaced X with something like Y, and you've lost X minus. Or we can choose the elimination path, and we can lose an equivalent of HX, form the alkene, and go through a totally different mechanism, totally different set of reactivities from nucleophilic substitution. So the question becomes, how do we choose, given a set of reaction conditions, whether we're going to do a nucleophilic substitution, whether that be SN1 or SN2, or are we going to do an E1 versus an E2 elimination pathway? And it really comes down to a couple different things. It comes down to nucleophile, so what we're actually attacking with. It comes with the alkyl leaving group, so whether that be an alcohol or a halide. And it really comes down to temperature. So what we see is that if we're examining nucleophile, if we have a strong base or a large nucleophile, we're going to favor elimination. If we have a small nucleophile or a weak base, we're going to instead favor nucleophilic substitution. So if we have a strong base, we're going to favor the elimination pathway. If we have a weak base, we're going to favor the nucleophilic substitution pathway. The size of the nucleophile also impacts that. If we have a large nucleophile, we physically can't fit in to do the backside attack or to do the attack at all on the carbon that has the X group that would leave. So instead, we're going to do an exogenous attack and pluck off a hydrogen. If we have a small nucleophile, however, we can do the backside attack or the attack to do the substitution pathway. What we see is for the alkyl leaving group, so we're examining this portion here, the CX bond. If we have a methyl or a primary alkyl leaving group, we're going to favor nucleophilic substitution. And if we have a secondary or tertiary alkyl leaving group, alkyl halide, alcohol, we actually run into the problem that it could do either, and we have to look at other conditions. So we have to look at the nucleophile, we have to look at the temperature of the reaction. So secondary or tertiary can go either way depending on temperature and nucleophile strength. What we see for temperature, if we're at room temp or cold, we're going to favor the nucleophilic substitution pathway. And if we have heat at all, we're going to usually favor the elimination pathway. So this is why to designate elimination in the last video, we usually add heat. And if you see heat, that's usually a good indicator that you're going to do the elimination pathway. So again, strong base is going to favor eliminations. Weak base is going to favor nucleophilic substitution. If it's methyl or primary, we're going to favor substitution. Again, we don't have that steric bulk blocking us from doing the substitution. And secondary or tertiary could go either way depending on the other reaction conditions. If we are at room temperature or cold, we're going to favor the nucleophilic substitution. And if we add heat, we will favor the elimination pathway. So now we're going to go over a couple examples, and we're going to predict the product and what pathway it's going to follow. So what we have here is a couple of examples of reactions that could be classified as either nucleophilic substitution reactions or elimination reactions. So what I want you to do for each of these is draw the major product and indicate whether it follows an SN1, SN2, E1, or E2 reaction mechanism. So if you want to pause, work through those problems, and then start the video again, and then we'll go over what the answers to these problems are. So, if we look at this first one, let's go through each piece and examine what we expect to happen here. So we have a primary alkyl halide, we have a strong base, we have a polar protic solvent, and we're at room temperature. Room temperature indicates that we're probably doing a nucleophilic substitution. Strong base indicates maybe elimination, but if we look at the alkyl halide, we are doing we are at a primary alkyl halide, so that's probably going to be a nucleophilic substitution. So we're going to do a nucleophilic substitution on the iodide. So this would follow, we're going to do nucleophilic substitution on the iodide, replacing it with an OET. And if we're trying to decide between SN1 and SN2, this is primary, so this is going to be an SN2 type mechanism. We wouldn't form the primary alkyl halide in this case, or the primary carbocation is just too unstable. If we look at the second one, we have a secondary alkyl halide, so that's one of those examples that could go either way, elimination or nucleophilic substitution. We have a strong base and we have heat. That is an indicator that we're going to do an elimination reaction. We have two choices. We could do the terminal alkene or the internal alkene. Since this is a small base, we're going to do the Zaitsev product, so we're going to form the internal alkene. And since this is a strong base and it's an alkyl halide, this is probably going to be an E2 mechanism. We're not doing a dehydration, and we're secondary, so we're probably going to be following an E2 mechanism. In this next case, we have an alcohol, and it's secondary, so that can go either way. However, we are in strong acid, so that's an indicator that we're going to do a dehydration. So our first gut instinct would maybe to put the alkene right here. However, if we think about the mechanism, we would form a transient carbocation that looks like this. And if we look next to the carbocation, we see that we have a quaternary center. We can do a methyl shift, putting the carbocation here, which would indicate that we would form not a disubstituted product, but instead a tetrasubstituted product. Since we have the OH2 leaving in one step, it's unimolecular, this would be an E1 mechanism. So we do have the carbocation shift in this case, so this is something to be careful of. Looking at these three, since you do have ethoxide, which is a strong base, you may have a minor product that is E2. And this E2 reaction, you might have a minor product that is SN2. But if we're looking at the major products, we would definitely see that SN2 predominates and E2 predominates. In this case, we would definitely have an E1 reaction. I didn't indicate that there's water or any other nucleophile around, so this would be an elimination type reaction. In this one, we have a primary alkyl bromide and we have a water molecule. Water is not a strong base, it's not a strong nucleophile, but we have a primary alkyl halide, so we're probably going to do a nucleophilic substitution mechanism, so we'd be left with this alcohol. And since this is a primary center, we can't really form the carbocation, so this is probably going to be an SN2 type mechanism, and we'd be left with an equivalent of HBr at the end. All right, moving on to this one, we have seemingly two functionalities, but remember that methoxide will only be a leaving group, like alcohols, will only be a leaving group in the presence of acid. We don't have acid, so we're looking again, OTS, that's that tosylate leaving group, that's a good leaving group. It's primary. We have a good nucleophile and a polar aprotic solvent, so this is an indicator that we're doing a nucleophilic substitution. And polar aprotic solvents indicate that we are going to be doing an SN2 type reaction mechanism. And azide is a good nucleophile, tosylate is a good leaving group, polar aprotic solvent, that indicates SN2. In this last example, we have a secondary center, we have a good leaving group, we have a strong base, and a polar protic solvent. This is all pointing towards an elimination reaction. So we have two options. We can pluck off the hydrogen at this tertiary center or the hydrogen at the secondary center. But we look and we see that butoxide is a large, bulky base. So that means that we are going to force to the Hoffman product, not the Zaitsev product, so the less substituted product in this case. So instead of forming the double bond here, we're going to form the double bond here. So this would be a Hoffman product because it's the less substituted product. And since it's a strong base and a good leaving group for the dehydrohalogenation, this is going to follow an E2 mechanism.